Okay, where we were, the last lecture, we finished with the breakdown. Basically what we were talking about was PN junctions, PN diodes, and we had discussed it in open circuit. There's no load on it, no source connected to it, forward biased, reverse biased, and then we saw breakdown phenomena. Now that's probably the device that I've gone into in most detail and will go into in most detail. Because of the lack of time, we'll just sort of skim through the rest of the devices that I'm interested in teaching about. And the next one that we'll take up is known as a bipolar junction transistor, or a BJT. We use the term bipolar, and there will be some devices we'll look at which are unipolar, and the distinction will be based on the fact that here for current to flow, it will pass through both N-type material and P-type material, whereas in unipolar devices, it flows through either one or the other. So that's the basic distinction between the two types of devices, bipolar and unipolar. Now in a bipolar transistor, we can either have N-type or we can have PNP. And what we will do is to look at the NPN type in this lecture. Basically, the NPN transistor consists of two diodes, one an NP and the other is a PN. They are back to back, combined together in the same device. They are not simply two diodes that are made and separately put together. The whole fabrication is such in a layer by layer growth structure as to allow us to create something of this nature. The connections are as follows. You've got one connection to the N-type layer here called the emitter. So E is emitter. And then you've got collector. And you've got B or base. Okay, these are the three basic connections that we have to the NPN transistor. Now, as far as the different materials that are used, they're all they're all silicon, or they're all the same kind of material, but they're doped differently, and even the thicknesses are different. I haven't sketched it to any scale, but it turns out that when you look at these, the emitter is heavily doped. Large, if you want high current density, that's the one that's going to serve as your source of electrons. It's heavily doped. The base, on the other hand, is lightly doped for reasons that we will see later. So that central region is lightly doped. It also turns out to be very thin. And by that we are talking of the order of something like 10 to the power minus 5 to 10 to the power minus 7 meters. Micron, from 0.1 micron to about 10 microns. In that range is what this number means. So it's lightly doped and very thin. The collector also turns out to be fairly lightly doped, though that is not as critical as the other two stages. Now we'll consider how this looks like the band picture in the unbiased case. And as before, we start off, given that it's unbiased and everything is in equilibrium, the Fermi level is the same throughout. On the left, we had an N-type material, so we are close to the Fermi level there. In the middle, we have a P-type material, and then again you have N-type material. So in P-type material, this is my valence band, right? Here we have got the conduction bands. So it's N, P, and N. So what we have here then is a structured, oops, I'm really way off maybe. That will look like this in the unbiased condition. The Fermi level is the same throughout, and we have the following structure. Now there are different ways in which these can be connected up. And when we make use of terminology here, what we mean by, say for example, EB, when I'm talking about that part of the junction which is related to the emitter and base, or we may also refer to it occasionally as the emitter junction. Strictly it is the emitter base region. We can just refer to it as EB junction. Correspondingly there, BC will then be the base and collector diode, and we will just call that the collector junction. Now you may make use of something like this either as an amplifier or a switch and so on. There are different ways in which this can be used. Now if you're going to use it as an amplifier, for example, as the name implies, when you give some input signal, you get the same signal amplified in the output end. And in that case, what we use is to use what is called a common base configuration. And in this case, the emitter base junction, which is the NP part of it, is forward biased. And the base collector junction, which is the PN part of it, is strongly reverse biased. Okay, so this is the configuration, and we can sketch it again now. I'll try to be a little more, the base region is narrow, so we'll make it that way, and you've got a heavily doped N type or N plus it may be, because it's heavily doped. And then you have the appropriate space charge layers at this junction, and you also have then the space charge layer for this junction. That's P, that's N. And what we have is that the emitter, this is the emitter connection, and this is the base. This is forward biased, which means we've got something like this. And for the collector then, through some external component, if I draw it, we have a reverse biased case, so it's, let's say something like that. That's the positive end. And there is a common ground. So the input signal is put in on this side, the emitter side, and we expect an output signal, which we will see is an amplified signal. So we'll get on the output side here an amplified signal. Okay? So let's draw the band picture for this one after it has been biased, and in this case it's going to look something like this. As usual, my drawings are not the best, but they will serve. And what we have now is that because the emitter base junction is forward biased, it's easy for electrons to go in this direction, right? And over here, because this junction is reverse biased, when it comes in here, it will be accelerated further. So let's call this the N, P, and N. So we have this is in forward bias. So from equilibrium now it's easy. Electrons from emitter climb over the lower barrier and enter into base. Now here is the thing, that in the base, I said that the base is lightly doped as well as very thin. And here are the reasons for that. That the base is going to be very narrow, the region through which it will go before it hits the space charge layer on this side. And so it's climbed here, and through a very narrow region of the base, it's going to have to pass. Now, because it is lightly doped, the recombination with holes in the base is less. So that's one possibility, that when they enter into the base, the neutral region of the base, that they can recombine with holes. So by lightly doping it, you try to minimize it. And secondly, by keeping it very thin, you increase the possibility that the electrons that are entering into the base make it into the depletion layer of the base collector circuit. And when they come here, the field is such that it will be accelerated down very strongly. And it is this acceleration that is causing the amplification, because here it has to cross the barrier, but once it enters into this depletion region, it's going to experience an acceleration down that. So as long as this is very thin and we don't lose too many to recombination, the electrons that are injected from here will enter into the depletion region here, where there is a very strong acceleration for the electrons. The gradient is such as to cause the electrons to be accelerated. So in the space charge layer connected with the base collector circuit, the electron is accelerated. Okay? So that's the fundamental basis. From here, by using a very small change here, we can get a much larger change, because you're going to be accelerated there and have higher velocities. Now we can look at that a little bit more closely, how it is actually doing the amplification. When we think in terms of the resistance in this area, because the base, the emitter base region, this area is, especially the emitter is doped highly, we have resistance somewhere here of the order of 10 to the power minus 3 ohm centimeter, low resistance. Okay? And in this region here, we have a much higher resistance, say 10 ohm centimeter. And so 4 orders of magnitude difference. The current is roughly the same. So when you look at the power, on one side you got I squared R, where R is 10 to the power minus 3. On the other hand, you've got same I is roughly the same. You have a little bit of loss, but roughly the same I, and you've got 4 times higher resistance. So there is a big difference in the power between the emitter base circuit and the base collector circuit, and that is what is producing the amplification when we use it as an amplifier. The symbols that are used in circuitry to denote these, just to give us the symbol, you'll probably be familiar already. That's the base with the arrow pointing away from here to the emitter, and this is to the collector. I haven't drawn it very well as usual. It's an NPN. On the other hand, if the arrow points inward, you have the PNP transistor. Okay, both of these, it works on a similar principle, just everything is reversed now, and you have holes as the majority carriers in a PNP, whereas in the NPN, electrons were the carriers of the current. So we saw that electrons were transported from the emitter to the collector, and what this arrow is indicating then is the direction of current flow. So that's the basic idea behind the BJT. We can see also that by controlling the base, the bias on the base, the forward bias, how much we are applying on this area here, small changes here will result in large changes in the current that will flow through. So we can use it to modulate the current that is there in the base collector circuit by making small changes in the emitter base circuit. So we have ultimately current flow from emitter to collector. How much is flowing can be regulated by bias on the base. For large EB in positive bias, forward bias, emitter base circuit in forward bias, when that is large, then we get larger current flow from the emitter to the collector, and vice versa. When you decrease that forward biasing, then you get smaller current flow. And this is the basis for using such devices in, say, amplifying the voice. You have it in a circuit where our speech is taken it's a modulated signal. So whatever is the signal that is applied to the emitter-based circuit, the modulation that we have, it appears in the output side, in the base collector side, the same modulation, the way we speak, up, down, pitch, tone, and so on, but amplified. So that is the basis of using this for speech amplification and so on. Okay. Now one more thing I would like to discuss is the frequency response. Basically, at what frequency, what is the highest frequency at which I can get amplification? That's what this frequency response means. So for the device, up to what frequency can it be used where I can get amplification? And it turns out that the highest frequency at which we will get amplification is inversely proportional to the transit time of the electron through base. That's the limiting factor. Right? If it's going to take longer to get through the base, then I will get amplification only at lower frequencies. If I can shorten that time, then I can get amplification at higher frequencies. So that is another reason for the base being very narrow. If the base is narrow, transit time is smaller, frequency of getting the amplification is higher. So this whole device can be optimized to give us a very high frequency response. The next device that I am interested in discussing is called the junction field effect transistor, or JFET. The JFET is symbolized by the following. We now have, instead of emitter and base, we have source and drain. I'm sorry, instead of emitter and collector, we have source and drain. And instead of base, we have gate. Okay? So D refers to drain, S is source, and G is gate. And what this particular symbol is referring to is a N-channel JFET. We'll see why it is N-channel and what is a P-channel and so on. In terms of its implementation, what it will look like is, maybe I should use a better page there. You have the drain, which is connected through some metal contact, and you have the source, again connected through some metal contact, and you have a, so let's say in this case we're talking of an N-channel device, so the center part is N. Okay, into an N-type silicon, we create P-type layer. 2 P-type layers are diffused in. This is not what a real device looks like, but just that gives us an idea. And then again we have the contacts to the P-type, so that will serve as my gate. Okay, and here I have that my gate is connected to the negative, so it's reverse biased there. So this area here, this and this is my gate. This is the drain, and this is the source. And the drain then is also reverse biased. Okay? What happens when this is reverse biased here? We have a depletion layer around it, between the P and the N, which will look something like this. I'll explain the shape in a second. Okay. And what we have effectively created is the central area, which is the channel between the source and the drain. So electrons will go from here to the drain, which is positively biased here. But the channel is in between these two gate electrodes, and depending on what bias is applied to the gate electrode, the channel width, the channel depletion layer width will change, and accordingly the channel width will change. As this becomes larger or smaller, the depletion layers, accordingly the channel for the electron flow from the source to the drain gets affected. That's the basis of this device, that you're going to control the flow from source to drain by simply controlling the gate voltage. Okay. As far as the shape is concerned, these areas here are more heavily reverse biased because of the effect of the potential of the drain, source to drain biasing. So on this end, they tend to be, the depletion layer tends to be larger than on this end. Now we look at it a little more in detail. Now this is called a unipolar device. Okay? Because the current from the source to the drain passes only through one type of material. Even though we've got P and N, but the source to drain, everything is passing through one type. In this case, it's N. We could also have a P channel, JFET. But here, everything is through this channel only, and that's why it's referred to as a unipolar device. So because the PN is reverse biased, I will get that as I go on increasing the voltage, okay, the depletion layer gets more and more larger in reverse bias between the PN. It's a PN junction that is reverse biased. We just saw in the last lecture that the depletion layer gets wider in reverse bias till some point is reached where this gets completely shut off. It's sort of like a gate that is closing. That's the name, a gate that regulates the flow. You know, dams where water is flowing from one side to the other, you can open and close these gates, and how much you open and close them determines how much water goes through. Similar idea here. So as the biasing on the gate is increased, as it becomes more and more reverse biased, eventually a voltage is reached when you have completely cut off the channel. And that voltage is referred to as the pinch-off voltage, Vp. This is the voltage that is applied to the gate. At that point, no current will flow through. So when Vg is equal to the pinch-off voltage, no source to drain current. Even there's no current going to go through the drain circuit. But when Vg is equal to 0, that means the gate is not biased. You've just left it intact without biasing it. In that case, what happens? You get maximum current through the source to drain, because the channel width is now, there is no depletion layer. If gate is not biased, that you have no biasing there, there is no, very small, I won't say no, but very small depletion layer that is there as our equilibrium value, the built-in value, W naught, and then you get the maximum current. So this is how we regulate it. You apply different voltage, increase the negative voltage, and you will get a different one. So this is also referred to as a normally on device. So if you do nothing to the gate, it's on. If you apply a voltage to it, it goes off. So that in that sense, it's referred to as a normally on device. It is also referred to as a depletion device, depletion type device, because it is the depletion width, the depletion in the channel that is regulating the flow there. And again, we have the idea is very similar to a BJT, that if you modulate the gate voltage, instead of having a simple change, you can apply some modulation to it on this circuit here. You will get the modulated value on the other side. Very small change in gate voltage, very large change in the source to drain current that we can see. So we can get the same kind of amplification behavior even using a JFET. If you use a P-channel JFET, everything is similar except that the gate is N-type material and the channel is P-type, as the name implies, and all biasing is reversed. Reverse means it's opposite of the previous case. But in principle, it behaves in exactly the same way as an N-channel JFET. The symbol that we have is again very similar, except that the arrow is pointing the other way and you have the source and drain. Okay? Now we come to another example known as the MOSFET. I'm just going through the various devices. As you see, it's a rather quick overview rather than any details which you can get from a semiconductor device class. It's basically the acronym, the abbreviation MOSFET stands for metal oxide semiconductor FET, or field effect transistor. I was drawing a blank there, pardon me. Field effect transistor. Metal oxide semiconductor field effect transistor. And we'll see some variations of this also. There are many names that come. Now again, for this, the depletion type is there, which we'll look at first. And the symbol for that, of a depletion type MOSFET, is the following: source, drain. We have now some connection called body, and then you have a gate. Okay, a source, drain as before, body and gate. Now what this looks like really in implementation of a real device will look something like this. I say I have a P-type substrate, and at the bottom we have a connection which is the body. And then there is an N plus layer here and an N plus layer here. In between these two is an N channel. On top of this, we have a metal connection. One source, one drain. And then we have the gate, which is also a metal connection here. I'm sorry, I missed I think I have to redraw that, otherwise it will not come out properly. Give me a second. Let me redraw that. I missed out the oxide, which is part of the metal oxide semiconductor. All right, we have the tubs as before here, N plus, that's not a problem. We have the metal contacts to source and drain. There should be an oxide layer here that isolates the different contacts. You have the base, the body as before. And then on top of this oxide you have the metal contact, which is the gate contact. And between these two, as I mentioned before, the N channel. This is the depletion type MOSFET. The source and drain areas are highly doped. That's why we've indicated them as N plus, and that facilitates good contacts. Can you suggest why? from what you might remember of Schottky and ohmic and all that, if this area is n plus, why will we get good contacts? How does, let's say, barrier height vary with doping concentration, or does it? How does barrier width change with doping concentration, if at all? Don't remember. We'll be going off on a tangent if we go too far. But basically, the width of the, yes? No, it's the opposite. It's 1 by root ND. Okay? As the doping concentration increases, the barrier width decreases. The height is not affected, at least not significantly. So what that means is that when you have highly doped areas, when you put a metal to it, because the barrier is thin, tunneling can take place. So even the barrier may be high and electrons can't go over the barrier, it doesn't matter, it will tunnel through because the barrier is thin. And that's why these are made as highly doped areas. The channel is the same type as the source and the drain there, but it is lightly doped. They're all the same type, in this case N. If you have other kinds are there, we'll have, that will all be P type. The substrate itself is a P substrate, in this case, and that serves as the body, support to the all this, and it is the opposite type to whatever we have for source, drain, and channel. So if your source, drain, and channel are P, then the body is N. And then this oxide layer that we have between the gate and the N channel. In other places, it simply serves to isolate different parts, but here, for the current to flow, it has to flow through this oxide layer. The oxide layer is thin, it's only of the order of, I think I have it written down somewhere else. We'll come to that. I think it's only 0.05 microns or something like that, of that scale. And because of the presence of that thin layer of oxide, the impedance there is large, and so gate current, which is really loss, if a current goes from source to gate, that's a loss in terms of the current that is going to drain, that is reduced. The same was the case with the BJT. If it goes from the emitter base and flows in that circuit, any of the recombination there was a loss instead of going to the collector circuit. And so if the base region was lightly doped, we did not have losses there. The same kind of idea. Here also impedance is high, so very little current will flow in that. It's just going to modulate things, but it's not going to have any much current flowing through that circuit. And as we can see here, the channel width is going to be controlled by the voltage between the gate and this body. If we make the gate negatively charged, okay, we apply a bias so that the gate is negatively charged, then electrons are pushed away from this channel into the P. They're repelled by the negative charge there, and they're pushed away from there. What that means is then that the N channel is less conducting between source and drain, because the channel is partially depleted. So by biasing it negatively, the gate, we get a partially depleted channel, lower current chances to go between source and drain. As it becomes more and more negative, what will happen? If I go on making the gate more and more negative, it is negative, it is causing some repelling of electrons, and so depletion. What will happen as I increase the gate biasing in the negative? Eventually, the same idea of pinch off as we saw for JFET. There's no electrons in the channel left to conduct between source and drain. Conduction stops, and so that same concept of pinch off is there. The channel got pinched off. So in this case also, as in the case for the JFET, if I do nothing to the gate and I just leave it unbiased, current will flow, maximal current will flow between source and drain. As I increase the negative bias on the gate, it eventually gets pinched off. So this too is a normally on device. Or because of the depletion there, it is again another depletion type device. And when we look at its characteristics, we will see that as we increase, this is gate voltage and this is the drain current flowing from source to drain. So as we go in the negative direction, we find that eventually at some voltage it gets pinched off. So no more current flows between source and drain. We can have another kind of MOSFET that is known as an enhancement MOSFET. And the symbol for that is, again we have the gate there, that's the body, source and drain. In this case there is no channel, so when we look at its implementation in a device, excuse me, we've got the P substrate, I got the body connection, and I got the source and the drain. And then there's the oxide layer as before. With the gate, except that there's no channel here. So since there's no channel and there's the source and the drain separated by a p-type substrate, what would you think in the normal condition without any biasing on the gate, what would happen? What is that? It's off, right? So in the absence of any biasing to the gate, nothing is going to flow between the source and the drain, and in that sense this is a normally off device. But now instead of applying a negative bias to the gate, we apply a positive bias to the gate. And when we do that, effectively we repel holes from below the gate. Yeah? And so eventually you also attract some of the electrons into that layer, and we begin to get a conducting path between the source and the drain. So some holes are driven out beyond some value of gate voltage. Initially it is repelling the holes. Some of the electrons are attracted in here, and beyond some threshold voltage called Vt, we will get then a conducting path between the source and the drain. So this layer that is created in the p-type substrates, where there are actually electrons that are built up there, it's like almost like there's an N layer there, is referred to as an inversion layer. It's p-type substrate, but there's a bunch of electrons that come here, and that's called an inversion layer. When you look at the characteristics of such a device, Again, we are looking at the drain current versus gate voltage, except that in this case the gate voltage is forward biased. And so what we will see is that beyond some voltage, Vt, which is the threshold voltage, we start getting current. Below that it's off. Above that it is on. Now MOSFETs in various forms, this enhancement, depletion and so on, are the most predominant technology used in IC fabrication today. It can be used for all kinds of applications, including memories, logic circuits, amplifiers, and so on. So MOS technology, we'll see another term, CMOS, is the predominant technology that is in use today. Again, when we think of the design of MOSFETs in general, one of the things that remains true as compared with the BJT also is that to get a high frequency response, channel length must be small. The time that it takes to go from source to drain, there it was from emitter through the base region, from emitter to collector. So here's the channel length, that is the critical term, must be small. So when we design MOSFETs, we should keep channel length small. The other thing to remember is that the channel width must be also small. To reduce the area of the device. And I give a simple illustration of some device parameters. Channel length may be something as small as 1 micron. Width could be a few microns. You understand what I mean by width, right? Not the depth to which it is going, but physically on the surface of the device, what is the width? Okay? And then oxide thickness we saw earlier, something of the order of 0.05 microns. P substrate doping is low. The typical metals that are used as the contacts, aluminum is the most common one. You can also use doped, highly doped polysilicon. You'll find this term polysilicon. I don't know if I used it before. Basically, polysilicon refers to polycrystalline silicon. And if you use it, you can deposit it. If it's highly doped, it functions like a conductor. Even though it's silicon, it's not a metal, but when it is highly doped, it behaves like a conductor. Another option is tungsten. These are some of the ones that are in use. Or some silicides like titanium silicide, molybdenum silicide, and so on. Here's a whole bunch of terms that are thrown in the literature. You have N MOSFET when the channel is N. So this is, say, for the depletion type. When we have channel is N, it's called an N MOSFET. It's a P MOSFET if the channel is P type. And when you have both N and P channels devices on the same chip and used in series, then it is known as C MOSFET, where the C refers to complementary. That means basically both N MOSFET and P MOS on same chip and in series. Actually, it's the CMOS technology, as it's called, which is really the dominant technology in IC fabrication. And the reasons for that are numerous. One is that very low operating voltage is enough. And whenever you think of computers and a lot of things, that's one thing you worry about, at how low voltage can you operate these, 0.1 volts somewhere there. Low power consumption. And as a consequence, heat released is low. So you don't have to worry about cooling down the chip and so on as much. And thirdly, CMOS technology is high speed technology. We also have something called a BiFET, which is a combination of bipolar transistor with a JFET. Then we have something called the MOSFET, or modulation doped. I won't go into it, but it makes it very fast. Modulation doped FET, very fast. Instead of MOSFET, sometimes people use the name MOSFET. You're almost tempted to say misfit, but MOSFET, where instead of, the idea is that it's not necessarily an oxide, it's some other kind of insulator. So basically there the meaning of it is metal insulator semiconductor, where you may have replaced the oxide with some other kind of insulator. I'll go through one kind, which is known as the MOSFET, which is not related primarily to silicon technology, but to gallium arsenide technology. And MOSFET means metal semiconductor FET. I'll do that very quickly and we'll close with that. In MOSFETs, the whole idea is there's a great demand for higher switching speeds. And what we have is, with silicon technology, you can have some 10 to the power 9 seconds, nanoseconds on-off times kind of that are possible. But if you want to go to higher speeds than that, then you have to look for some material which has got higher mobility. Okay, so mobility is the velocity in per unit field kind of idea. So if some material is there with higher mobility, we can use it. So mobility is the driving force for these high speed devices. And gallium arsenide, it turns out, has got a 6 times higher electron mobility, if you remember some of the numbers that we looked at. So that seems a very promising candidate. The only problem is that the hole mobilities are approximately the same. And what that might mean for us in terms of design of some kind of a device where we want higher speed is that we should try to make use of only n-type gallium arsenide, because then everything will be running with electrons and we'll make use of the actual high speed. And the device that is used is known as a MOSFET. Basically, we make use of a semi-insulating gallium arsenide substrate. By semi-insulating, we mean it has a very high resistance. It's chromium doped. Chromium introduces some levels that cause it to become semi-insulating. And on top, we have an n-type gallium arsenide active layer. Nothing else is there. You got source, gate, and drain. With respect to the source being at 0 volt, the gate is negatively biased and the drain is positively biased. And this layer is very thin. Now, when you put a metal onto a gallium arsenide, if you choose the metal correctly and make this a Schottky junction, the gate, What do we have below it? A Schottky junction sitting on an N-type gallium arsenide in reverse bias. What can we expect of the gallium arsenide here? I don't have time, so I'll answer depleted. Right? It's in reverse bias, so we have depletion there. So what that means is for current to flow from here to here, it's going to pass through this depletion layer. And if we bias it strongly enough, and this layer is thin enough, then the depletion layer will pinch off with respect to the semi-insulating gallium arsenide. So this layer becomes completely depleted in this area. So as you reverse bias it and more, eventually, because current is not going to flow through the semi-insulating part of it, that's a very high resistance. So the N-type active layer that is there gets pinched off because of the reverse bias that we put on the gate, and as a result, there's no current flowing. So here we are making use of only N-type gallium arsenide in the active part of the device, and so we can get very high-speed devices. That's the normally on type. You have to apply some bias there, and it pinches off. Okay, I think I will stop with that. There are other kinds of devices that we can talk about which are related to optoelectronics, LEDs, lasers, and so on, but that's a whole different topic.
What is the fastest device which you have
right now? I have no idea. The fastest speed?
I mean the fastest switch.
I don't know. Guinness Book of World Records or the internet?
No sir, actually somebody was asking.
You can probably look that up, but it will be based on some technology like this MOSFET or MESFET or something like that.
Actually, research scholar was talking to me. He had this problem only. So